Hello. Today, I'm going to be talking about Newton's law of cooling as an example of modeling with first order ODEs. And I'm also going to be talking about solving autonomous first order ODEs graphically, or getting a qualitative feeling for the solutions. All right, and that's like webwork sets 5 and 6. All right, so what is Newton's law of cooling? Newton's law of cooling says that the cooling rate of an object is proportional to the temperature difference between the object and the ambient temperature. The ambient temperature is kind of a fancy word for just room temperature. Okay. All right, here's an example. Suppose a coffee cup is filled with 90-degree C coffee in a 20-degree C room. So I like to use Celsius, and room temperature is very close to 20 C or 68 degrees Fahrenheit. And we all know that water boils at 100 degrees C, Celsius, except when we're on a mountain. Water actually boils at about 93 degrees up here in Flagstaff, C, 93 C. So we pour this coffee in the cup at, we'll call it T = 0. And then initially it's cooling down at a rate of 3.5 degrees C per minute. Okay, so find the temperature Y of T in degrees C at time T hours. So even though we gave the cooling rate 3.5 degrees C per minute, time T is in hours. All right, so let's start here. I'm gonna have to erase this soon, but let's start by rewriting what it says. It just says that the cooling rate, dy dt, that's the cooling rate, is proportional. You know, that kind of symbol looks a little bit like an alpha. Okay? But it's proportional to the temperature minus, it's often called A, the ambient, oops, not T, it's Y. We're using Y. It's proportional to Y minus A. Okay? And that's what this law says. The rate of the cooling rate, dy dt, because Y is temperature, T is time. And this is going to be degrees C per minute. And it's going to be proportional to the temperature difference. Give myself some room here. So, in other words, we're going to say that dy dt is equal to a constant times, in this case, y minus 20. And that constant is going to be a negative constant, right? So I'm going to actually call it minus k. And then, since k is positive, okay, right? Because if the object, like the coffee cup, is hotter than the ambient temperature, hotter than room temperature, then it'll be cooling down. dy dt will be negative. Okay, so we're not sure what k is, but it'll be a negative constant there. Okay. So what we're saying here is that dy dt for this problem is equal to negative 3.5 degrees C per minute when y equals 90. Okay. Okay, and I'll call it, we can put in degree C. We're a little bit, sometimes we put it in, sometimes we don't. So sue me, but hopefully it's all right. Now, if y is measured in degree C and t is measured in hours, this has units. This has units, degree C per hours. Because units of dy dt are units of y, degree C, with units of t hours. So what we have to do here is have to turn this into degree C per hour. So we have, what is it, 60 minutes over 1 hour. Okay, and we can say if. All right. All right, good. So that means that dy dt is minus 3.5 degrees C per hour if y is 90 degrees C. So this is going to be going to be enough to find out what k is. So let's before I erase the rest of the problem, let's put in the initial condition. Y of 0 is 90, right? Because that's, see, when I say initially starts cooling. Initially, it's 90 degrees, right? So I know that this is, I know that this part's kind of difficult, but turning these words into the equations is a real useful and important skill. All right. And I know it's kind of tricky. So anyway, so let's now, we can figure out what k is. Oh, I screwed up. 3.5 times 60. And that's degrees C per hour. I forgot that. Okay, all right, so that's from the description of the problem, but it's also equal to minus k times 90 minus 20, right, from the Newton's law of cooling. From this ODE above. So I set them equal and solve for k. Minus 3.5 times 60 equals minus k times 70. All right, so that means k is minus 3.5 times, sorry, minus k, well, let's just write. So k is, the two minuses cancel. K is the positive 3.5 times 60 over 70. Right? So it's 3.5 times 6/7. Okay, what is that? Okay, 7 times 5 is, let me see. 3.5 is 3 plus a half. 6 halves plus 1 half is 7 halves. So this is equal to 7 halves times 6 sevenths is 7's cancel, 6 over 2 is 3. So k is 3. All right, so what we get is, is the differential equation that I told you I'd be talking about for almost the whole review. That's our differential equation. dy dt is minus 3 times y minus 20, and y is 0. I don't need that anymore. And y is 0 is 90. All right. So let me do actually one more way of solving this differential equation. I've done several now. But this is, there's kind of like by inspection. But this way I'm going to talk about now is maybe what I really think when I do this. This is the same thing as the derivative of y minus 20. That's the same thing. The derivative of a function of t, y at t minus 20, is the same as dy dt minus 0. The derivative of the constant is 0. Okay. So what it tells me is the rate of change of the temperature difference is minus 3 times the temperature difference. Okay? And you don't have to do this, but we could say let u of t equals y of t minus 20, and this just becomes du dt is minus 3u, where u is the temperature difference. Okay, we don't want to use d because d is for derivatives, right? So this is by far the most important ODE, right? U is u naught e to minus 3t by inspection. So this is sort of like a little thought bubble. I just write down y minus 20 is some constant times e to minus 3t. Okay, or y is 20 plus a constant e to the minus 3t. Cool. So we've got another way of getting this general solution. Very similar to the first thing I did, just kind of guessing and checking or solving by inspection. All right, but let's figure out what c is. Y of 0 is 20 plus c times e to minus 3 times 0, and we're going to set that equal to 90, because y of 0 is 90. But e to the 0 is 1, so 20 plus c is 90. Therefore, c is 70. Okay? So the solution is y is 20 plus 70 e to the minus 3t. All right. So let's graph that. Let's graph that. So here, if I put, so I'm just gonna go time from 0 to 1 because, right? 1 hour, I mean, I'll probably have drank the coffee by the time 1 hour is up. And let's go from here, 0 to 100 in temperature. Give myself a bit more room. I guess we're done with that. Yeah. So, all right. So so that we have here is 50. Here's 20. All right. So we've got this. We've got this constant solution, but I start here at 90, and I approach the constant solution. How fast do I approach it? Well, here's 30 minutes. This is t in hours. This is called half an hour. Here's a third of an hour. Here's a half an hour. Here's 2/3 of an hour. 20 minutes, 30 minutes, 40 minutes, etc. So after 20 minutes or a third of an hour, this becomes, let's just say this. So y of a third of an hour is 20 plus 70 times e to the minus 1, right? Because 3 times a third is 1. So e to the minus 1 is about equal to 3 to the minus 1, or 1/3, right? So when I get to here, a lot of thirds, the initial temperature difference of 70 degrees, here is 90 here, starts out at 90, The initial 70-degree temperature difference get multiplied by a third. It's around here somewhere. Okay, so that's pretty much what the temperature looks like. This is the coffee cup that I didn't drink, cub. And then this is the room temperature here. The room temperature stays 20 the whole time, okay? And in fact, let me say a little bit more on this. Newton's law of cooling is this. Restated. Okay, Newton's law of cooling stated a different way is this. Okay, the temperature of an object decays exponentially to the ambient temperature. I'm going to get rid of this. I'm going to call it room temperature. You can call it ambient temperature if you want, but that's really all that Newton's law of cooling says. And Newton, he understood calculus pretty well, right? And for him, these two statements are really kind of the same, right? If you understand solutions of differential equations. The solution says that you have the room temperature 20 degrees C, and the temperature of this coffee cup just decays exponentially to 20 C. In fact, it's kind of useful. I erased that because I wanted to draw, I said C before, that was really Y. Okay, here's the room temperature at 20, and I'm going to draw a dotted line. Here's room temperature 20. No matter what the coffee cup is, I don't have to think about one of them, I can think about all of them at the same time. No matter what the initial temperature is, the temperature will decay exponentially to, in this case, 20 degrees, right? Okay. So let's do another, think of another way of doing this. Now there's this other set, which was how to solve something like, these are autonomous equations. Something like this, dy dt is f of y. This is an autonomous first order ODE. And what is it about autonomous first order ODEs? Well, for one thing, we can always solve them by separation of variables. If I can do the integral, but right, I can do dy over f of y equals dt. So the ODE is separable. But integration is hard. And we don't need to do the integral. To get qualitative information about the solutions. So quality of the solution, not necessarily the quantity. We're not going to be able to necessarily find the functional form of y of t if we don't do the integral. But we can probably do something better. We can understand the problem. Okay, let's get rid of this. The first thing when you have something like this is the equilibrium solution. So if y, see y of t there is a function. So this y star is a constant with f of y star equals 0. Then we say that y of t equals y star is an equilibrium solution. To dy dt is f of y. Right? So these are the values of y that give me constant function solutions, right? If the initial condition is y of 0 is y star, and I plug it into here, then dy dt will be f of y star or 0, and that solution will just stay put. I'll get a constant or equilibrium solution. Okay. And then we can get a rough sketch of solutions by considering just the sign, SIGN, plus or minus sign of f of y. Okay, let's do an example. Anybody guess what the example is going to be? Yep, dy dt is minus 3 times y minus 20. This whole thing is a function of y only. No explicit t in it, just of y. Okay? So Newton's law of cooling doesn't say that, in the year 1668, something happens and 10 years later there's a different rule. The rule has no explicit time in it. All right, so what I do is I plot now versus y. Look at y. That's y, and I plot dy dt. What does dy dt, or which is our f of y, look like as a function of y? Now this is a linear function of y, pretty easy to graph. It's not in the mx plus b, I guess in this case it'd be my plus b form, but it is in a slope y-intercept form. Okay, that's kind of funny, y is horizontal, right? I put in here, here's 20. At 20, this function of y is 0, right? So this right-hand side as a function of y has a horizontal intercept of 20, slope of -3. There it is. Right? Good. Does that make sense? All right. So that means that y, okay, that means that y star equals 20 is an equilibrium solution. Okay? If I take this object here, that's at room temperature, and I measure its temperature as time goes on, it will be at room temperature now. 10 minutes later, it will still be at room temperature. This is at an equilibrium temperature. Everything in this room is, right? Except for the coffee cup. All right. So also, you notice that we see this if y is bigger than 20, then dy dt is negative. So if y is bigger than 20, dy dt is this line is below the axis, so dy dt is negative. We knew that so the object is cooling down. Well, I guess we don't really know what the interpretation of this is, but okay. And if y is less than 20, then dy dt is positive. All right, so I can take that and actually get a picture. I'll do it. I'm going to do it in my orange here. So in orange, I'm going to say, on the y-axis, what happens? Some people like this. I could actually draw a little picture here of y. The arrow tells me where y goes, how y changes as time increases. Right? So there's a little picture. In fact, that's often called a phase portrait for this. Okay, so here's a little phase portrait. Here is y, and here is 20. And then that's the picture. This is a phase portrait of that thing. I don't see the time there. In fact, this arrow here, maybe I should even leave out that arrow. That was increasing y. So we'll leave that out. This arrow is how a solution moves as time advances. In fact, later, the very end of the course, we talked about phase portraits where again we didn't draw a t. We had, say, x and y, and we had dx dt and dy dt, and what we just drew, these little lines talking about what the trajectory of the solution is. Well, this is like that trajectory, except we're in one dimension, one dependent variable instead of two. Okay? All right. So we can also do this thing. We can do this. We can also, I don't want to use the orange. We can also get what the solutions look like from this picture. What the solutions look like as a function of t, right? And if here I put t and y, I know I've got to turn it on its head, but if I think about t versus y, oh, there's this 20. There's a solution. That's the equilibrium solution. That's y equal 20 for all t. That's a solution. If temperature is above 20, I decrease. Temperature is below 20, I increase. Okay. All right. And this kind of makes sense for the Newton's law of cooling too. If I don't have a coffee cup, but I have a cold drink, soda or something that's colder than room temperature, the temperature will increase and approach room temperature as time goes on. Whatever the temperature, above or below the room temperature, as time goes on, the temperature of an object decays exponentially to room temperature. And I know this might not look like decay, but this is really also, at least mathematically, a decay toward the room temperature of 20. The temperature difference decays to 0. All right. Okay, so one more thing about this is that we can also think of the slope field for this problem. And rather than trying to draw it, I'll just go to our app here. Let's share the screen. All right, here's our favorite program. All right. So here's our slope and direction fields app. We're going to change variables to dy dt, and we're going to put in -3 times. Okay, and I don't really need the times. -3 times, maybe I should do it, times y minus 20. Okay, and then I click on this. Whoa, okay. It does not, it's kind of hard to see what's happening. I just see a bunch of vertical lines, okay? So let's see what's going on here. Uh, well, first we're talking about temperature in a room and stuff. 20 degrees is nowhere on here. So we're going, in fact, this is freezing Celsius. In fact, Newton's law of cooling for the coffee cup doesn't work for a coffee cup filled with ice, right? Frozen stuff. But anyway, so let's change y to something more like 0 to 100. So here we go from freezing y equals 0 to boiling, okay, y equals 100. The other thing is we're looking about a scan of 8 hours here, the time interval. So let's go from time 0 to 1 instead. 0 hours to 1 hour. Okay, now it starts to look a bit more reasonable, and I can put in exactly our situation. I guess y of 0 is 90 and submit that. Okay, and if you look at that, you notice it's a little bit, I can see the curves here. When I go from 0 to 1, that time interval is too big. I should probably do maybe 0.01. Looks a little bit better. And then also Euler's method is pretty lame. It changed a little bit from Euler's method to Runge-Kutta, and it would have changed a lot more if I had kept it at 0.1 for the step size. But okay, so here's what the temperature looks like. And we can also put in lots of other initial conditions. Let's put in, we'll submit in green the temperature of the room. There's the ambient temperature. It stays put. That's the equilibrium solution. Or I can put in other temperatures above and below. Okay, room temperature. So I have either warming up to room temperature or cooling down, okay?